Once again, I would like to welcome all the participants for being in this program. And today the topic I have selected is role of geospatial technology and expert systems for optimal utilization of input resources in precision agriculture. So as I have already told myself, Junaid Nazir Khan, I'm a professor in College of Agricultural Engineering and Technology from Skosh, Kashmir. So basically about the overview of this presentation, I'm going to discuss four things in this. I'm going to discuss you about precision agriculture as it is written in the title itself. I'm going to tell you something about optimal utilization of input resources. And I'm also going to discuss about role of geospatial technologies and expert systems. So starting from the precision agriculture, I think this is the third day or fourth day most probably you are having in this training program. So you must be knowing about precision agriculture. Just for the introduction, I'm going to say these things. So when you talk about precision agriculture, three things come into your mind automatically. One is the production, another is the productivity, another is the profitability. So precision agriculture, you can say, is related with three P's: production, productivity, and profitability. You must have heard just few days back. I'm just going to give an example of all these things. Few days back, I think most probably on 1st of June, World Milk Day was celebrated. And this is celebrated every year. This is celebrated, and for the last 20 years, it is being celebrated. And this 1st June, this on this particular date, what the example I want to give you is that the milk production in India, as you must be knowing already, that India is the largest producer of milk in the whole of the world. And if you see the statistics about the production, 22% of the world of the milk production in India is done by India. Of this milk is done in India. And if you look in these things deeply, if you want to look in this, next country is the USA, which is at the second number. We have the largest milching animals in India. We have the largest number of the milching animals. But when you talk about the productivity per animal, it is just 2 liters per animal per day. And if you compare it with the country that is at the second place, that is the USA, and you will be surprised to know that they have a productivity of more than 8 liters per animal per day. Maybe some states may be having higher, but if you talk about the overall average of the country. So from this, you can see that there is a lot of potential, especially in precision agriculture, because there are many factors why the productivity is low, especially if you're talking about the milk. What is the reason for that? One of the reasons that I could find is that because of non-availability of proper fodder, because milk production is related to the availability of fodder. There are number of times when there is no availability of fodder, and I think especially if we talk about our conditions during summer months, there are many lean months when we don't have any fodder availability, or if you talk about plains and other regions. So it is a kind of a complex situation, and the solution to these is in this, because these are all interrelated to each other. If you talk about different branches, if you talk about agriculture, horticulture, fisheries, there are so many branches, and all of them are related to each other. I will give you one more example. And our university has very recently developed a variety of paddy, and they say those developers, those genetics who have developed it, they say it has a yield potential of 9 to 10 tons per hectare. Paddy, you must be knowing that it is rice. So, but actually, when you give that variety to the farmer in the field, on the university farms, it is attaining this yield of 9 tons per hectare. But when you give the same variety to the farmers, they say we get a maximum of 4 to 5 tons or maybe 6 tons. So you can see there's a lot of yield gap. What is the reason for that? Maybe because of management. You can say the management is not proper in that. Maybe that is one of the reasons for that. So again, talking about it, so these are the things especially we have to take care about, and I think this precision agriculture is exactly these things we will be talking about it. And my topic will be specifically related to role of geospatial technology and expert systems. So I will be also taking a few minutes about input resources in agriculture. So these are the basic input resources in agriculture. If you talk about them, number one is when we were young and we were doing our BTech, it was told that the most important input resource in agriculture is the seed. And that was very true also, because if you go back into the history, you will be seeing that the green revolution took place because when good quality seeds came from outside, they had very high yield potential, and the this seeding material was also very good. So at that particular time of the green revolution did take place because of the input resource, that was the seed. That was the we were talking about the seed. Now, second, another very important resource in this is the water. Water is a very important resource, and when you talk about the water, if you see the water, we talk about the term in agriculture, that is the water use efficiency. That means how much amount of water that is coming from a source and it is to be given to the plant. How much amount of the water is actually being utilized by the plants. And if you see on an average, you get a water use efficiency of just 33%. So the water use efficiency is not much high, depending upon the present situation what we have. Talking about drip irrigation, sprinkler irrigation, and other things, they have a high water, but normally the water use efficiency is very low. And seeing the situation about water, you can see that the things are not very good in this direction. I can give you another example. I'm going to share with you about this. You must be knowing about saffron. Saffron is a crop that is grown in this UT of Jammu and Kashmir. And if the saffron crop, the yield of the saffron crop, if because it's a rain-fed crop, it is at most of the places it is a rain-fed crop. And if all things go well, it doesn't have a disease, and you get the labor on time, you get the fertilizer on time, you get all the things on time, then you will be having a yield of 3 to 4 kg per hectare. So, but our university has identified some critical stages in the growth of the this crop, and it has been found that there are some 4 critical stages. And if you are able to give irrigation to the crop, to the saffron crop at these 4 stages, the yield jumps from 3 to 4 kg to 8 to 9 kg, even up to 10 kg. And as you know that saffron is a cash crop, and a lot of profits are involved in it. A farmer who may be earning 6 lakhs per hectare will be earning 12, 13, 14, even 15 lakhs for that crop. So just by giving water at the right time totally changes the whole scenario. And it's also true about the fertilizers. The fertilizers you give to the plant. If you give the fertilizer at the right time, in the right quantity, in the right amount, things are totally changing from this. Now, another important factor is the soil. It is again a very important input resource in agriculture, and not many people are talking, but especially from the Himalayas. We are from the Himalayas, the northwestern Himalayas. I will just give you an example about. You must be knowing that erosion taking place from the agricultural lands I'm talking about. You must United States Department of Agriculture some 50, 60 years before gave a table telling us about what is the erosion that is taking place from the agricultural field. So they made a table. It is well established. It has been approved everywhere. So when the erosion is in the field is between 0 to 10 tons per hectare per year, we say erosion is in the normal range. But when it jumps from 10 to 20 hectares, we say erosion is very high. And when it jumps from 20 to 30, it goes on in that, and they have established that table up to 80 tons per hectare per year. This is they say more than 80, it means it is a very serious kind of erosion that is taking place. But over the experience, we have seen that, especially in our region, that we are having erosions up to 250 tons, 300 tons, 350 tons per hectare per year. So you can see that it is dying a slow death. We are dying the kind of the things we are doing with our soil. It is totally this kind of thing is happening. We are slowly dying a slow death because of not doing proper management of our resources. And that is also true for when you lose the soil. That means agriculture is finished, and all the nutrients, you are losing all the nutrients, whether it is organic carbon, it is nitrogen, it is phosphorus, it is potassium, and all these things you are talking about, you will be losing all these things. Now, I was very recently, I was checking a thesis from a student from Punjab Agricultural University, and he was telling about he had done some research work in the Salera watershed. I think most probably that is in the Hoshiarpur district. And I think in Punjab, at the foothills of Shivalik Range, there are a number of small structures which store water in them. And he was telling that what he had interpreted using this Geospatial Technologies, getting erosion of 60 tons per hectare per year, such a high value of the erosion he was getting from this, and the reservoirs that can be used for storing water and that are giving water for so many years to people. And within the hypothesis he was telling, depending upon different parameters, that within 20 to 25 years, all of them will be filled with silt and sedimentation, and ultimately we won't be having anything available for storage in that structures. So taking proper care, I'm giving so much emphasis on these input resources because these are all dependent on agriculture, and agriculture is nothing without these resources. Now, again, pesticides. When we're talking about pesticides, we are also talking about fungicides. Pesticides means when we use it for stopping the pest. Fungicides means when we use it for stopping the various diseases, which are so predominant these days. And also the weedicides. These are all big problems, and we lose a lot of means a lot of crop. If we talk about diseases, 29% of our crop is lost in the diseases. And if you talk about these weeds, 30% of our crop is lost in weeds. So all these things have to be managed in a proper way. Just a few days back, I was seeing that a simple lining material, it is a kind of a polypropylene lining material that is put on the plants, and if you give 5 6 these plant production, if you give pesticides formulations to the plants by using polypropylene, you will be able to reduce it from 5 6 to 2 3. 2 3 You have to give so much amount of sprays to the plants. Now, another is the labor mechanization. Again, this is a very important input resource in agriculture, because when we talk about agriculture, agriculture is all about timeliness and precision. As you might be knowing that out of 141 million hectares, the arable land that we have, that is cultivable land that we have, about 48% is irrigated and 52% is rain-fed. And when we are talking rain-fed, that means we don't have any irrigation facilities for that area. And if you don't give if you don't have a mechanization inputs in such kind of agriculture, you won't be able to grow crops in these regions, because when there is a rainfall, then you will have to go for sowing of the crops. So it is all interlinked, and it is all dependent on each other. And the last one I'm talking about is the technology driven agriculture. And it is very important why I'm saying that what you have been discussing for the past few days, and I personally have an experience about it, whether it be Internet of Things, whether it be wireless sensors, whether it be soilless technologies, whether it be protected cultivation, whether it be automation, whether it be robotics, ultrasonic sensors, robotic arms, so many things. And I think, like we were talking about seed in the 80s or 90s, the seed is so important for agriculture. In the present times, I'm saying that technology that is being discussed here, that what the organizers have thought about, is so much important that it is one of the, I can say that in the present situation, it is one of the most input resources in agriculture. And I think we are from the agriculture background, agriculture engineering background, but people from, because we don't have expertise in many things, be it computers, be it electronics. So unless and until we don't have such kind of interactions, joint collaborations, we won't be able to come with suitable solutions for it. And cost effectiveness is very important for all these things. I had been to Israel a few days back, and seeing the kind of investments they are doing in agriculture, it's mind blowing. So much investments they are putting in agriculture, and they are getting the results and benefits from it. As I will be discussing in my presentation, even if you talk about in protected cultivation, pollination inside a greenhouse, it is a small thing. Now firms have been developed for doing that thing also. That is a small thing. People are, and jobs are being created for that, doing pollination inside a greenhouse. We don't have such kinds of concepts over here. And I think in the coming times, all these things have to be taken care of. So precision agriculture, again, we'll be talking about the 5R. It is basically right input, right time, right quantity, right place, right manner. So basically, precision agriculture, if we talk about it, it is precision farming also, it is precision irrigation, precision fertilizer application, precision water application. So be precise in all the things, and ultimately it is going to have a benefit on your crops. Crops are going to be different when you do all these things. So right input at right time, right quantity, right place, and right manner. And it can be further taken if you talk about this precision farming: appropriate action at appropriate time, at appropriate proportion, so ensuring that quality and quantity of farm produce. So precision agriculture, again, I have talked about it, is to increase the crop yield, improve the quality of the products, make more efficient use of agrochemical products. When we talk about agrochemical products, these are the fertilizers, these are the pesticides, these are the weedicides, these are the fungicides. They all play an important role in agriculture. And if they are not managed properly, your agriculture is going to be affected in a huge way. And also, it is a very important thing, most people don't discuss about it, is the protect the physical environment against pollution. So, and taking care of the environment is again very important. Develop such things that we'll be talking about. And say energy saving is also a major objective in this direction. So you can see the figure. I have taken. These are two countries I'm talking about. One is Syria and another is Israel. And you must be knowing that these are both adjoining. These are neighbor countries. On one side is the Israel and another side is the Syria. And you must have heard about Syria for the wrong reasons. There's so much of civil war going on there, and so many people are dying there. And if you look introspect deeply in what happened in Syria, and people have done it, and you can see that this is Aleppo, Syria. There was a drought in this region, this Syria, from 2006 to 2011. For 5 years, there was a very severe drought. And immediately after that, what happened? People started migrating from one place to another, and all sorts of things happened. And you can see after 2011, even up to, it has been almost now 10 years, you can see total destruction has taken place in the country. People have migrated from one place to another. So much of damage has been taking place in this. And on the other hand, you can see to Israel, you can see these figures. This is from the Israel. I had been there for some 2-3 years back. And Israel also, there was a very severe drought there was in Israel from 2000, I think 14 to 2018, 19. There was a very severe drought in Israel. But if you see on the ground, because of the kind of investment they did in agriculture and in other things, you see, it didn't affect them at all. You must have heard about the Lake of Galilee. They also call it as a Sea of Galilee, who has been to Israel. And they say that its levels were they say they were the lowest of the levels they had. There were people saying that it is just a kind of a joke. They were saying that Jesus Christ, he is a prophet. What he used to do is that he could walk on Sea of Galilee because he had that miraculous powers he had with him. So he used to walk on Sea of Galilee. It's a big Galilee and a source of fresh water for them. And now they were saying that everybody is going to walk on the Sea of Galilee. Do you know why? That was just a joke. They were saying that everybody is going to walk on the Sea of Galilee. Can anybody say me why they were saying like that? Am I audible? Anybody? Am I audible, sir?
Yes, sir. Yes, sir. You are audible, sir.
Yes, sir, audible, sir.
Okay. So just for this, I was saying that because they were saying that there will be no water in Sea of Galilee. That is the kind of the drought they had there at that particular point of time. but afterwards the things did improve. But what I want to say, you can see these two figures. This is the Israel Negev Desert. It gets a precipitation of just 30 mm per year, which is almost negligible. In our state, we had this Ladakh region, and it gets a precipitation of 152 mm per year, and we say that it is a arid region. Means we get very less rainfall in this region. And you can see this in this Negev desert, they have totally transformed it. It's just like a golf course. You can see that is because of the technological interventions that have been done, especially the modern engineering inputs that have been put into agriculture, and they totally change. And that is the need of the hour. In our case, this is the need of the hour, that we have to invest in this direction. Many people, there are many critics also who say that on one hand you are talking about investing so much in agriculture, going for drone technology, going for automation, going for all kinds of things. And the other hand, you can see that farmers just destroying their produce. If there's a lot of produce we have of tomatoes or potatoes, especially in Punjab region, you can see farmers taking that and throwing it into the dustbins. So that thing is also there, but the times that are going to come, we have to take care about all these things in the future. So talking about, since I'm a waterman, I will be talking more about water in this. This is when to irrigate and fertigate. So like human beings, plants don't know when irrigation is to be given to them, and also when fertilizer is to be given to them. When we talk about fertilizers, there are 16 major nutrients or fertilizers that are to be given to the plants. And irrigation, when to irrigate the crop, that's very important, because plant is not going to tell you when to irrigate it. And you must have heard about the story of drip irrigation system. As you know that in the present times, the irrigation system was developed in Israel. Sincha Blas was the chief engineer in Israeli company. He says that once a farmer came to him and he told him that, "Sir, I want to show you something." And when he went to the farmer field, he saw maybe it was a quinoa field, this or an orange field or some other field. I don't remember it exactly. And he said, "I want to show you a tree, one of the trees, and in that tree the yield was the maximum. The characteristics, overall characteristics of the plant were very good in that tree." And he said, "What is the reason for that?" So what they did, they began to dug that root zone of the tree, and they found that one of the pipelines was leaking water in drops to the adjacent to that tree. So that is where from the drip irrigation came. And after that, this Sincha Blas left his job and started a company. You must be knowing about the company. It is Netafam. It is a very famous company. It is units all over the world. In India also it has. Netafam is the company. And they started this was the purpose for that. That is when to irrigate the crop. What is the normally there are methods of doing this, but nowadays the making use of the sensors. When we were studying our PhD or other things, we made use of tensiometers. A tensiometer is a device, basically it measures the metric potential. It measures the metric potential of the soil. That means if you talk about the metric potential, it means what is the force that is required by the plant to extract water from the soil. So that is the metric potential. And tensiometer was a very simple device to use, and you could tell it. But nowadays, making use of the sensors, and there are so many sensors available nowadays, that can tell you when to irrigate the crop. And also the fertilizer. And the second thing is how much to irrigate. Again, a very important role is to be played. There is the background that if you have, because it depends on so many factors, what is the type of the soil, what is the depth of the soil profile we have, and how much also on the field, what is the field capacity of the soil, what is the saturation point of the soil, what is the permanent wilting point of the soil. All those people who are related to the agriculture field, they will be knowing that normally that water is to be given when it should be at the field capacity level. But when it goes away from the field capacity, maybe 10%, 20%, 30%, 40%, 50%, depending upon, it varies from the crop to crop, and you have to give irrigation and the quantity of irrigation to be given. Then also the fertilizer, how much fertilizer you have to give to the plant, what is the quantity of the fertilizer, what is the frequency of this fertigation you have to give the plant, at what frequency you have to give it. So all those things, there is a lot of research has already been done for number of crops. Now we need to have some interventions from the engineering side, especially pure specialists who have knowledge of this and who can use their know-how in this direction. Now, talking about methods of irrigation, what are the different methods of irrigation, whether we use sprinkler irrigation, we use drip irrigation, or other methods like that. Now, atmospheric and weather indicators. Supposing you have to give irrigation to the crop. So how you do it? Nowadays, you will be talking about you have a temperature sensor, you have a humidity sensor. Based on that, seeing the temperature, humidity, the radiations, all those things, when you count together, you can, on those basis, you can tell when you have to irrigate the crop, taking these weather parameters into account and giving irrigation to the crop. Crop indicators, depending upon the health of the crop, what is the color of the crop, what is the, what we call, what is the thickness of the stem of the crop, what is the temperature of the crop. All these indicators are being used for doing this kind of irrigation. What is the when to give the irrigation or how much amount of irrigation that is to be given. Then there are also the soil indicators. Now, just I was talking about the tensiometer. When you take a tensiometer and put it into the soil, it will tell you when you have to irrigate the crop. Or if you have a moisture sensor uh, connected to a data logger, you can see that when you have to irrigate the crop and how much irrigation you have to give to the crop. So all these things have to be taken into account. So now talking about the fertilizers, again, you must be knowing that there is a lot of subsidy on the fertilizers, and it, if you talk about it, goes in thousands and thousands of crores, the amount of subsidy that is given the fertilizer. And when you talk about the fertilizer use efficiency, just 30%. Even nitrogen is the main fertilizer in the form of urea you are using. Very low fertilizer use efficiency. That is, we are not using things to its potential. And if you can see from the table that India ranks second in the world fertilizer nutrient consumption, next only to China. 14% share in world fertilizer consumption. Fertilizer consumption in India has increased manifold over the past 4 decades. Per hectare consumption still low compared to neighboring countries. For example, China is 433 kg, Bangladesh it's 252 kg, Pakistan 131 kg, India 144 kg. So you can see that uh, that there's a lot of potential, I am saying that when we talk about the yield, if we talk about any variety, we talk about the potential of that variety. What is the potential of that variety? There's a maximum level we can. So there's a lot of potential. You can say that we can improve to a lot extent we can improve it. You are all engineers. Can anyone tell me what is the efficiency of a diesel engine that was developed by Rudolf Diesel? Anybody? I'm sorry, I'm not able to see the chat box. If anybody can, just not to make it monotonous, speaking from one side. Am I audible, Sarjeet?
Sir, you are audible, sir.
But nobody is responding. I don't know why. Maybe
It,
my lecture is not very good.
no, sir, you are going very well, sir.
And I was just
Yes.
talking about what is the efficiency of a diesel engine.
It's around 43%, sir.
43%. You are talking about the present diesel engines. But when Rudolf Diesel developed, it was just 22 to 22%. So almost they have doubled over the years. They have almost doubled. And that is especially what I'm talking about when I'm saying, I'm repeating again and again about water use efficiency, irrigation, fertilizer use efficiency. So these things, and they cannot be achieved without engineering inputs. I'm telling you, with the experience I have, it is not possible to have these things with the engineering inputs. So you can see this. This is a these are low cost, because we talk about here about jugaad. These are low cost technologies we are talking about. This is most probably, I think, from Hyderabad. You can see this is known as the alternate wetting drying tubes. And if you must be knowing that for 1 kg of producing 1 kg of rice, you take 3,000 to 6,000 liters of water. The range is too much. Somewhere it is 3000 liters, somewhere it's 6000 liters. But if we are using only 3000 liters, that means you are saving a lot of water in paddy. If you see this farmer in the field, he is using this very simple device. It is a PVC pipe. I think about it will be 30-40 centimeters in length, and it has been holes have been put in that part that is in the soil. And when you put into the soil and lift the soil, it gives you the level of water in the field. And research has been done. They say that when water goes from the surface, it goes below 5 centimeters, it goes down, or it goes 10 centimeter down, or 15 centimeter, or 20 centimeter down, then you will have to irrigate the crop. By this way, you are saving a lot of water. You know that water is very important. By this simple, this you can say this is an irrigation scheduling kind of a device that we have, just to see what is the level of water in the paddy field and planning it accordingly, depending upon the depth of the water, whether we have to give water, at what depth we have to give the water. And so this kind, I think this will hardly cost some 100 rupees, this kind of irrigation scheduling device that we have in this field. And you can see here also, this is a water meter, or to measure the quantity of the water that is to be given to the field, because it is very important. I was I think some 2-3 years before, I had gone to Saudi Arabia, and there is one district there. They call the water that is available there as fossil water. Fossil water, they say, because there is no because of the climate change and all these things, it is not being recharged. That means they say that this water is going to last for, say, 20 years, 30 years, or 40 years. But in spite of the fact, when we actually see what is happening, we calculate the amount of, because depending upon what is the water requirement of the crop, how much water does the crop need, and how much water do we give it. And even in such circumstances where water sources are fixed, we know that they are going to get finished in 20-30 years. And the law of the nature says that we have to use it judiciously, we have to use it optimally. But even under such circumstances, people are not doing it. They are giving water as per their requirement and not seeing what is the requirement of the crop. Are we giving more water to the crop? Are we waterlogging the crop? Doing such kinds of things. So that cannot be achieved without the engineering inputs that we are talking about. And you can see here, this is a small partial flume with a very simple mechanism for measurement of the water. Basically, it measures the discharge of the water and how much water is to be given to the field. So this is a case study from Hyderabad, I think. Very small and we can say low cost technologies that have developed. Solar power is used for operating this system. We have this Arduino SIM battery, temperature and relative humidity sensor, basically telling us what I was talking about, the irrigation scheduling, when you have to irrigate the crop. It will be telling you about that. Then also the ultrasonic sensor, it will be telling us about the depth in this flume, what is the quantity of the water that is coming in. And all these things, this whole thing will be operating at the real time. All these things will be opening at the real time, and people are using this kind of technology, low cost technology, actually to be adopted by the farmers. Actually, that can be adopted by the farmers. And in real time, we will be knowing what is the quantity of the water that is to be given to the field. So again, as I was already telling that this about nutrient and fertilizer management, I told you that we need about 16 elements for growth of the plants. They have been classified as basic nutrients, major nutrients, secondary nutrients, micronutrients, and optimal nutrients.
So that
Some may be
antenna
in
you
large
can see
quantities
over here,
and some.
and this is just an overview of this station. Next, we have a different kind of channel that is present in our
There's a,
communication. Now, to understand this
I think
concept
Tarun,
of forward channel, reverse
please
channel,
mute
or
Raj
control
Kumar.
channel, let us consider that this is our base station,
Tarun,
and here we have, let's say, mobile.
okay, thank you very much. So about nutrient and fertilizer management, I was talking about the basic nutrients, uh, carbon, hydrogen, oxygen. They are available in the air, carbon, hydrogen, and you don't have to give it to the plant. But talking about the rest 13 elements that are the major nutrients, nitrogen in the form of urea you give to the plants. A lot of urea is being given. Phosphorus is being given to the plants in the form of, and also potassium is being given to the plants. And different kind of fertilizers we have, say muriate of potash, and so many. I don't want to discuss them in detail. So you can give these kind of fertilizers, and giving them in the proper proportion. Giving them in the that is very important. How much amount you have to give? As you must be knowing, in drip irrigation system, we have the, or sprinkler irrigation system for that matter, we give both water as well as fertilizer to the plant, and we can give all these nutrients in the right quantity to the plant: nitrogen, potassium, then the secondary nutrients, calcium, magnesium, sulfur, then the micronutrients, boron, zinc, iron, molybdenum, manganese, copper, optimal nutrients, sodium, silicon, nickel, cobalt, and all these. And if the soil is, if you don't have these kind of nutrients in the soil, it is ultimately going to affect your productivity of the crop. And how much to give it, and also to identify that by which method we are to give it. All these things are researchable issues that have to be taken care of. I was talking about this fertilizer use efficiency. About nitrogen, when we talk about soil application, when you directly apply fertilizer to the field, you get a efficiency of 30 to 50%. Phosphorus just 20%, and potassium it is 50%. And in case of drip irrigation system, you get a fertilizer use efficiency of 65%, and phosphorus you get 30%, and potassium you get 60%. And when you talk about drip plus fertigation, when you have a system where you apply fertilizer as well as give this water to the plant, so you will be getting a nitrogen fertilizer use efficiency of 95%, and also phosphorus you will be getting fertilizer use efficiency of 45%, and potassium it will be 80% on an average. So now this is a slide that I have taken from my PhD research. You must be wondering why an old man like me is showing such an old slide when I was doing my PhD some 10-15 years back. So I did my PhD on drip irrigation system, and that too on Goa. And if you can see this, you can see this slide. Under drip irrigation system, the yield I got is 68.7 kg per tree under drip. And for when we use the drip irrigation plus the fertilizer application through the drip. And control means when you do it normally, how farmers are doing it. They just give water to the crop, and you get a it is as 37.01 kg per tree. And this MI2 F2, we had different treatments in this field. M is here represents the mulching, and we had different treatments of irrigation because we were using tensiometers for giving irrigation to the crop at different soil metric potential. As I was already telling you that I1, when we have this much amount of this much amount of the force the plant requires to extract water from the soil, and similarly I2, this much amount of this force, or we can in terms of metric potential we say it in kilopascal, this much amount of force you need to extract water. Similar way you see this. And similar the fertilizer application. What is the quantity of the fertilizer you have to apply? What is the amount of fertilizer you have to apply to the plant? I was giving urea, I was giving phosphorus, I was giving potassium to the plants. And the purpose of this is you can see how it affects the productivity. And I'm telling you, when you give irrigation to the plants, there are two important things that have to be kept into account. You have to give irrigation before sunrise or sunset, because then only it will have a good impact on the crop. In case of my crop, it was the guava crop. And second thing that is to be taken care of is that this is when we do all these things manually. I remember that doing all these things manually is a very tough job. If you have, supposing I had 100 plants at that particular time, and I had 20 plants under one variety, 20 plants another variety, so it is so cumbersome. I think when I used to give irrigation, sometimes I had to give irrigation myself. I used to get up at 5 o'clock in the morning, and each plant was operated by a control valve. Every plant has its own control valve. Supposing if you have to give I1 treatment, 20% this metric potential to the plant, so you'll have to open only those kind of control valves to give irrigation to the crop. Similarly, if you have to operate the second treatment, say the I2 treatment, you will have to give this much amount of irrigation to the crop. And similarly for I3, you will have to do it in. Similarly for fertilizer, you have to manage this. For a simple, this is a common problem experienced by all the this what we call this uh, people working in the agriculture field, and especially for a farmer. If you develop such kinds of system, I think it is 100% guarantee that they won't be using such kinds of things in this. So again, you can see from this, by using a simple intervention in case of drip and fertigation, from control from 37, we got an average of 68.7, and the best treatment almost 100 kg per tree we got because of using this kind of input, we can say, as a drip irrigation as an input in this. So this is one of my students have very recently done this. This is about hydroponics. I think you must have discussed about hydroponics for the past few days also. About basically when we do hydroponics or soilless cultivation, we don't use soil in that. That is one of the things. In hydroponics, we grow in water. Aeroponics also, there's a mechanism for that. I think you must be hearing about it. Supposing you have to select if you have to go for this growing of the seed, you don't need soil for that. So you will have a medium that is better than the soil. So in this case, selecting from many, supposing we have cocoa peat, we have coconut husk, we have perlite, we have sawdust, and out of them selecting from so many, you have to select that kind of the medium that is best suited for that. And in her case, for the lettuce crop, she used a combination of two mediums, that is sawdust and the rock wool. And doing this combination, she found that the best result she got in this sawdust and the rock wool. And they were covered with a polythene prior to filling with sawdust. Cups filled with sawdust up to 2/3 of the volume. Seeds were individually placed on the sawdust layer, and using Grow Cube 333 rock wool cubes of. Am I audible?
You are audible, I guess. There is some problem at his end.
What is sawdust?
Sawdust is basically when you the byproduct you get when you saw the wood. It is the sawdust. Sawdust is that. When you cut the wood, the powder you get, it is the sawdust. It is the sawdust. So this was the medium she used, rock wool and the sawdust in a combination, and all the net cups were placed in the plastic tray, disinfected, because this is you have to standardize things. If you are doing something, there's a lot of knowledge in the literature also, but trying to standardize things, disinfecting with 70% ethanol, and don't put it in the direct sunlight, using fluorescent lamps for growing of this nursery. And two techniques: underprotected cultivation, that is in a greenhouse, these things are to be done, or a polyhouse. When we say greenhouse or a polyhouse, when we use polythene instead of glass, we say it as a polyhouse, and we use the polyhouse for it. And you can see this nutrient film technique. It is a lot of information you will have in literature also about it. In these pipes we grow this constant flow of nutrient through the channel, circulating hydroponic system, plants placed in channels with root danglings in the nutrient solution, continuously recycled nutrient solution, reservoir or holding tanks, submersible pumps, net pots to hold plants distribution, and these are all, and no aeration equipment is needed in this. And there was another system that is known as the deep water culture. Deep because the depth of the water is more in this. It exceeds 8 inches, non-circulating hydroponic system, also known as a passive system. The root remains submerged 24/7. And container components is container to hold water, net pots to hold plants, aerator to oxygenate the water, lid to cover the nutrient solution, modular system comprising of 6 growth tanks, plastic container served as growth tanks for the deep water culture system. And you can see from this figure, these are the length of the roots under 3 systems. CN is the conventional system. That means we take the plant and we take this lettuce and plant it into the greenhouse in the soil. Another is the nutrient film technique, and another is the deep water culture. And as you can see from the figure, in case of deep water culture, the root length is much more than it is in the conventional irrigation. That means You can play with the plants also if you want to increase the root depth, if you want to that way you can do a number of things in this. And just to share with you the information, you must be knowing that in case of wheat is also known as I think you understand wheat, kanak. It's also known as
Yes.
kanak.
Yes, sir.
It
Yes.
is,
Yes, sir.
if it is just like that wheat, if you put it the maximum root length in wheat can go up to 2.5 meters. So if it is not able to find water in the top layers of the soil, it goes on going down, down, down up to 2.5 meters. But in case of paddy, it is a kind of a genetic code. They have these plants of their own. If it doesn't get water up to 30, 40, 50 centimeters, it is going to die. But taking the case of the wheat plant, it has a kind of a genetic characteristic that it can go up to 2.5 meters down deep, and you can extract water from that depth also if there is a shortage of water or things like that. The same is the case here. You can see in the root development is much better, and as the root development is much better, that means the other things also change in this. So these are different data collection. I think she has used these kind of sensors for measuring electric conductivity, basically to see what is how the fertilizer solution is, because it gives it is an indicator of how the fertilizer is behaving in that system. What is the quantity of fertilizer we have in that system? Also pH. pH plays a very important role in the what we call when the plant has to take the nutrients from the soil or from the water or from any other medium it has to take. Similarly, what is the temperature of the system, what is the dissolved oxygen, and all these things, sensors have been used for that. And also measuring very different crop parameters. What is the crop duration parameter, what is the date of the sowing, days to emergence, days to reach two leaf stage, days to transplanting, survival rate after transplanting, days to harvesting. Then also crop growth parameters. What is the plant height, plant spread, leaf area, number of leaves, yield per plant, root shoot ratio, and also the quality characteristics. What are the proteins, fiber, dry matter, disease, and all those things have to be taken in that experiment. And this is the table. This is the graph showing how the electrical conductivity varies inside the system in case of both deep water culture system and the nutrient film technique. And you can see, we have seen it from the literature, that when it is maintained in the range of 0.8 to 1.6 decisiemens per meter, plants won't have any shortage of these nutrients. It is basically a nutrient solution. It contains all the nutrients, talking about which that crop needs. And it is readily available in the market. And based on the electrical conductivity, you can see that first daily she has been monitoring it, maybe even hourly, based on the data logger, seeing how it varies. And you can see after a few days, we again give the fertilizer solution. It goes on decreasing. Again, we give the fertilizer solution. It goes on decreasing. Again, we give the fertilizer solution. So you have to replace some 7-8 times. The graph itself shows that 7 to 8 times you have to replace the nutrient solution in this. Now this is the pH. As you can see that as the nutrient solution decreases, the pH increases. And again, for this particular crop, the pH should be in the range of 5.5 to 7. And if it is in between the range, the plant doesn't have any stress of extracting the nutrients. And if it goes above it or if it goes below it, it is going to experience stress. So you can see for total growing season how it varies, this deep water culture as well in case of nutrient film technique, how the pH got changed in this. Now this is what I want to share with you is the crop duration of this. Now I told you about three things we were using. One is the conventional method, taking the crop, planting it in a greenhouse and seeing how it is behaving. Second is the deep water culture. It is a hydroponic system used for growing of the plants. And the third one is the nutrient film technique. So first is the transplanting. Transplanting, in case of the conventional method, we did in the soil itself, and it took 35 days for transplanting. Days to transplanting is 35. And in case of deep water culture, only 22 days were taken to transplanting when we use the rock wool and sawdust in combination. And in case of nutrient film technique, it took us 22 days to transplant, and days to harvest in case of conventional 47 days, and in case of deep water culture 40 days, and in case of nutrient film technique 49 days. So from this table you can see that total growing days when you do it in a conventional way, because we are talking about off-season availability. And if I talk about my conditions in Kashmir region, you must be knowing that because of the very harsh climate we have over here, we have the agriculture growth for only 8 months. Only for 8 months we have this kind of agriculture. Even if we go to higher elevations, if you go to Ladakh, Nyoma, or other places, it is even lesser than that. So having these kinds of systems, supposing in conventional it goes to 82 days, and in case of deep water culture it is 62, and in case of nutrient film it is 71. So you can see that this kind of interventions, how they can play a vital role for off-season availability. We are talking about off-season availability, both before and after. Supposing some varieties we are developing, if they come into the market 1 month before, it is going to have a profound effect on the rate of that thing in the market. Total water consumption, you can see from that in nutrient film technique, because water is also an important, you can say, element in all these things. And you can say that the water in this is 1.094. Now, coming to this about the main topic I was to discuss with you, this was about geospatial technologies, the what kind of works we are doing at our place. You can see this talking about geospatial technologies, the GIS, the GPS, the remote sensing, all these things, especially they use in the agriculture. We are talking about this, the remote sensing techniques, airborne, ground-bound, space-bound satellites. I will be talking about basic applications. I won't be talking about much detail about the methodologies that have been used in this. Now, the trends in the application, the topographic map, the thematic mapping over the years, how things have changed, the geomorphology, geosciences, forestry, soils, water resources, widening of thematic disciplines, and it is the oceanography, marine, agriculture, fisheries, and how the things have changed over the years, and also the decision support systems, what we are doing in this field. Now, talking about, initially in my introduction, I told you that soil is a very important component in all this when you talk about agriculture as a whole. And if you are losing the soil at the rate of 250 tons per hectare per year, that means things are not very good, things are very bad. And this is one of the simplest equations that has been used for finding the erodibility. We call it as universal soil loss equation, that has been developed by United States Department of Agriculture for finding what is the amount of erosion that is taking place from the agricultural land. And it is an empirical equation. As you can see that the average annual soil loss, having a units of tons per hectare per year, it is dependent on rainfall erosivity factor. Basically, what is the intensity of the rainfall, what is the amount of rainfall falling per unit time, and quantity of the rainfall also. What is the quantity of the rainfall, is the duration of the rainfall, and soil erodibility factor, depending upon what is your type of the soil, what is the structure of the soil, what is the texture of the soil. When you talk about the texture of the soil, what is the percentage of silt in the soil, what is the percentage of clay in the soil, what is the percentage of other constituents in the soil, and the topographic factor, what is the slope of that, and what is the longitudinal slope of that, taking all these things into consideration. What are the crop management factors that are being, what is the land use classification in that area, and what are the conservation practices that are being followed in this. And based on this, taking all these things, because you have number of empirical equations by which we can find what is this R, K, L, S, CP, doing all these, merging this all, and using for this ArcGIS software has been used. You can come up with these what we call amalgamated kind of these thematic maps, where you will be able to know what are the critical areas where erosion is taking place. As you can see from this, red is the maximum amount of erosion we are having, just having a kind of, we have a interpretation what is the kind of the erosion taking place in this area. Now these are this is one of the studies we have done under externally funded project that was sponsored by NICRA ICR, This is a SWAT. SWAT is this has been developed by, again, United States Department of Agriculture. It is a soil water assessment tool. It is a very important. I think this is a free software. It is easily accessible. You can get it from the net also. It tells us about what is the runoff taking place from a particular field, and also what are the sediments that are coming from particular watershed. As you can see, this is the area of the Leh watershed. It is a watershed. You must be knowing it is an area which has a single outlet bounded by some particular it has some definite boundaries. And the area of the Leh watershed is 107.5118 kilometers square with 28 subcatchments. So talking about the SWAT model, it can be integrated with ArcGIS, also QGIS. It can be integrated. All the information, maybe it is the soil information of that particular area, maybe the rainfall information, what is the rain falling in that, and also the climatic factors, say the temperature, the humidity, the rainfall, and other things that are essential for this. They are to be known. They can be known from this, and also other parameters. You are talking about the land use, land classification, and if you have to this what we call tell the boundaries, the delineate the watershed. Those who are doing this kind of research, they might be knowing it. And ultimately, it tells you a lot of information about the average precipitation, average snow melt in that area, what is the runoff that is taking place from that area, lateral flow, what is taking place, groundwater contribution, recharge to deep aquifers, water moving to plants, and ultimately it will be telling you what is the total sediment load that is coming from that watershed. And this has also very good graphical interface. You can also see different if you talk about the hydrologic cycle, there are many things that are going in the hydrologic cycles, and you will be knowing basically what is the runoff that is coming from that area, and what is the sediment coming from that particular area that we have delineated, and we will be knowing the erosion, what is the erosion that is taking place, and accordingly we can tell about the various conservation measures that can be adopted in this. Again, this is again the output of this SWAT model I was telling you about. There's a very good graphical interface in this. It will be telling you about what is the runoff that is taking place, 31.28 mm per year. What is the sediment that is coming from this area, maximum upland sediment. And if you want to, because there are certain hydrologic response units in this, they will be telling you about each area, what is the kind of the erosion that is taking place, or what is the kind of the runoff that is taking place from that area. Is it clear? If anybody wants to ask, he can stop me. And so this is another, this is again done in a watershed. You can see special distribution of annual runoff under different climate scenarios, because nowadays we're talking about climate changes that are taking place. And in climate change, we have these RCPs, representative concentration pathways, different 2.6, 4.5, 8.5. And we can do such kind of studies in this, saying that if we have a scenario of RCP of 2.6, basically when we talk about 2.6 scenario RCP, that means what is the kind of these radiations that are coming in this particular area, 2.6 watt per meter square or 4.5 watt per meter square, RCP 8.5 this watt per meter square. Yes. I think there's a little bit of disturbance.
Dr. Binoy, please mute yourself.
So you can see from this, this is a climate change study that has been carried out in a certain micro watershed. Basically, we wanted to know what is the amount of runoff. Runoff means the extra water that is coming from that particular area. And also, what is the sediment? Sediment means the amount of soil that is coming from that area. And depending upon the climate change standard that have been fixed, as we are talking about RCP, concentration pathway 2.6, what is going to happen under those situations and how things are going to change depending upon what will be the concentration of carbon dioxide in the atmosphere. And you can see from this figure, some areas are showing a runoff 92.99.7, and another is showing 80.2 to 92.3. And if you just combine it, the observed, what actually is taking place from that is 86.38. And when we change it to the RCP scenario of 2.6, you get 96.41. RCP scenario of 4.5, it will be 98.96, and RCP scenario of 8.5. And percentage changes as compared to the observed, it will be increased 11.61, 14.56, and 25.30. And also average sediment losses tons per hectare, what is observed, and other different climate change scenarios, what is the amount of sediment that is going to come out from that area. So again, you can see here another what is the amount of sediment that is taking place, by which we can identify those areas which have high erosion rates and come up with some suitable solutions where we can say that in this area we have so much of erosion taking place, and we can do, maybe we can go for plantation of trees in that, or maybe we can go for some engineering measures like go for check dams in this area and other things we are talking about. Now this is, if you can see this, this is a soil profile. This is the Hydrus software that is used for movement of water in the soil. How water moves in the soil based on the finite element. It uses the Richards equation for seeing the movement of water, not only the movement of water, but also the fertilizer movement in the soil itself, because it is not possible to see how water moves inside the soil. And here you can see that these various boundary conditions have been given depending upon variable flux, what is the discharge in this, and what is the atmospheric boundary conditions, the free drainage conditions. And using Richards equation, you can see actually these are all, I think most of the softwares are not being developed here that are actually practically in the use. They come, this Hydra software, this has been developed by Danish Institute, I think. And you can see in this case, if you see this shows the movement of the water. We have taken a soil profile of 100 centimeter depth and about 75 centimeter in the width. This is true in case of the drip irrigation system. In case of drip irrigation system, if you are giving giving water to the plant, and if you have to see after 4 hours what is the water availability of water in the different horizons, you can see in both, this comes also in the 3 dimensions, but this one is in 2 dimension, and you can see that what is the this water content at different places in the soil depth. So accordingly, on the basis of this, supposing you have to put a drip irrigation system, they come in all kind of capacities, supposing 4 liters, 6 liters, 8 liters, 10 liters, 12 liters. So you can decide what should be the discharge of that dripper and see depending upon the root depth. So how the water changes in this and for how much time it is going to last in the, and you don't have to manipulate the soil profile. You can do it for this kind of a this kind of a variety, that what is how many drippers you need for that, what will be the movement of water in the soil, how soil is going to move, and all those things. Now also the fertilizer movement. This is the nitrate movement in the soil. As you know that nitrate is the major contributor of this pollution to the groundwater. And in this case, after 4 hours, after 8 hours, after 24 hours, after 48 hours, depending on this, what the results we get, what is the concentration we have, how much quantity of fertilizer we have, we can come up with the solutions. As I was talking at the starting of my lecture, what is the quantity of the fertilizer you have to apply, what is the quantity of the water you have to apply. So this kind of software, this kind of decision support systems play a very important role in telling you that this much amount of water is to be needed, this much amount of water is to be given, this much amount of drippers. In case of drip irrigation system, this should be the discharge, whether it should be 2 liters per hour, it should be 4 liters per hour, it should be 6 liters per hour, and this is the amount of fertilizer we have to give. this much amount of ppm of fertilizer we have to give, so that there will be increase in the irrigation water use efficiency and ultimately the fertilizer water use efficiency. So this is, as you might be knowing, that in our region we are famous for apple. Apple is a very important crop in our region. And you can see this is a table that has been taken by from Department of Horticulture, Kashmir. In 1953, the area under apple production was 12,400 hectares. But if you see in 2017, the area has increased to 3,38,528 hectares. So you can see it has increased many times. Many times it has increased. And you know that land resources are limited. That means if there is a conversion, it is going, earlier some other crop was grown in that area, now it is being replaced by some other crop. And the main reason for that is, the major reason for is that because of greater profits you get in apple cultivation. So people are shifting from, say, somebody is growing paddy or rice he is growing, he will shift to he will go for horticulture, he will go for growing of almonds, he will go for growing of apples, he will go for growing of pears, because a farmer wants more profit from whatever he is doing. So you can see the changes that have taken place in this over the years, and it is still increasing in that way. And this is the one of my colleagues have done this study, historical and the future projects of LULC. This is the whole of the Kashmir Valley they have taken. I think maybe satellite data has been used in this study. And you can see that the land use land cover in 1973, you just have to concentrate on two colors. One is the yellow color and another is the brown color. Yellow color is the agriculture we are talking about. When we are talking about agriculture, it is the paddy crop, it is the maize crop, it is the wheat crop, it is the oil seeds crop. That, and when we're talking about horticulture, it is the apple tree, it is the almond tree, it is the walnut tree, it is a pear tree. So based on this old Landsat images, he has come up with the land use land cover map, how things were in. And you can see agriculture was predominant in most of the areas, and horticulture was at isolated places. But as the time changed, in 1980, you can see more area under horticulture, and it is doing it on the basis of the agricultural crops. It means less of agricultural crops and more of horticultural crops. And you can see in 1992, you can see more, more horticultural crops are beginning to come in this picture. And 2008, again, you can see how things are changing. More and more of agricultural land is coming under horticulture land. Just concentrate on two colors. One is the yellow color and another is the brown color. And again, you can see, this is 2013, you can see the changes. I don't have to say anything about it. You can see how much area is under horticulture and how much area is under agriculture. And now simulated maps have been developed. Maybe he has done a study before. You can see this depending upon how much area is under horticulture and how much area is. Now these are all simulated maps now. Simulated map of 2040. You can see this, how much more area is under horticulture and agriculture is going on decreasing. Simulated map of 2060 and simulated map of 2080. You can see the changes. Changes are more predominant. And 2100, you can see that horticulture has taken over agriculture, and that is only because of the profits that the farmer is getting. He is planting more and more of his land under those kind of where he will be getting more and more profit, where he will be getting profit. He is doing like that. Now this is a figure. Basically, there are, if you can see in this figure, this is formerly a paddy land that has been converted into an orchard due to water shortage. This is a farmer, initially it was a paddy land, now it has been converted into an orchard. And similarly, thousands of canals are doing this. But the question is that if he is converting something into something else, is it feasible to do that? If a land has been earmarked for paddy, it has been doing paddy for the last 1,000 years or 2,000 years. Now he is changing just for getting the profits. And when he goes for a plantation, the investments he makes and then he finds that ultimately that he has lost everything. He has lost all the investment he has put in it. And also government also took a serious note in this. They said basically prepare a land classification map and see that particular crop. If we are growing this apple trees in, if we are growing apple trees in this what we call uh, in a paddy land that has initially been. Am I audible?
Yes, sir, you are audible.
Somebody is responding that he is not hearing. I don't know.
Yes, sir, we are listening to you.
Okay, okay.
I guess the problem is that his antenna maybe he's not able to.
Actually, sir, if we switch on our video, then there should be a fluctuation. So that's why we just switch off our video. Otherwise, we are listening.
I should switch off the video.
We all switched off video because it should some fluctuation if we switch on the video. If we people are switch on.
Okay, okay, okay. So you are talking about this. I was telling you about the conversion because there's a land capability classification. Again, it has been developed by United States Department of Agriculture. When we talk about when we have to do, if we are growing some crop in some soil, is it feasible to grow that crop in that soil? So it depends on number of land features, the soil characteristics, and the environmental factors we are talking about. Now, when we talk about the land features, it is the slope of the land, extent and type of the erosion, waterlogging, wetness, marshy land, etc. Then it is the soil characteristics. When we talk about the soil characteristics, what is the soil texture we are having? What is the soil depth we are having? What is the permeability, internal drainage, soil salinity, alkalinity, environmental factors, rainfall and temperature? They all decide whether a particular crop is to be grown in this kind of the land capacity classification. Basically, is this land suitable for growing this crop, or you are doing something not very we can call not very intelligent thing to do. Now, this is one of my students did the land suitability map for taking a certain area and seeing she's the crop, supposing for paddy is being grown in this crop. Is it a right thing to grow paddy in this particular area? Again, using remote sensing, GIS, all these different thematic maps she has been using in this and finding whether this particular area is suitable for this kind of crop. If you can see this, S2 is moderately suitable for growing this crop. S3 is marginally suitable, and in case of maize, the area this is not suitable, highly suitable, moderately suitable. Getting such kind, this gives an idea about the things. If we are growing horticultural crops in paddy land, is the right thing to do because you are changing something that has been going on for the last 2000 years, and now you are introducing some other crop. Will it, maybe not at that particular time, the farmer will not be facing that kind of heat, but maybe after 2 3 years he will be facing that kind of heat. So this is again the table that has been justified. What is the suitable land, highly suitable, moderately suitable, marginally suitable, and so on. So again, this is again a externally funded project we had, finding what is the status of the glaciers.
Hello?
Hello. Sir, voice is not clear. Hello.
Dilip sir, please inform Junaid sir, he lost the connectivity, I think.
Am I audible?
Yes, sir. Yes.
Yes, sir.
I think there was some problem. You can see the presentation?
No, sir. Yes, sir. Visible, sir. It is visible, sir.
Okay, okay, fine, thank you. So using doing these kind of studies, using list 4 image depicting an agricultural land, seeing what is the area that is being covered under different crops, getting an idea under different, doing a kind of the statistical surveys to see what is the area under different crops by using different satellite imageries, and also using images to see what is the snow and the glacier, and also water bodies. All these things can be used for finding these parameters. Now talking about, just to give you an insight about our state, you can see this Jammu and Kashmir state, and this has a total area of 2,22,236 square kilometers. Now it has been bifurcated into 2 union territories, Jammu and Kashmir and Ladakh, and out of that 35% of the area is under Pakistan administered region. Area with the China is 19.2, and in Indian region we have 45.6%. And why I am showing you this is because of the Ladakh area. It is, you can see from the figure, and this is the northwestern Himalayan region. You can see it comprises of the 3 states. One is the Union Territory of Jammu and Kashmir, Ladakh, and the state of Himachal Pradesh, which cover an area of more 1.5 lakh square kilometers. And you can, with a passage over the years, what is happening. One year we have a drought, another year you have a high rainfall. So all these things are happening. You are seeing the screen?
Sir,
Yes,
it is
sir.
visible.
And you are audible as well, sir.
Okay, thank you. So, yeah, these kind of situations are saying that government is saying people not to go for paddy cultivation because of non-availability of water. So such kinds of things are creeping in. And you can see this is in the Ladakh region. Just by in one of the projects we are doing, you can see three figures: 2015, 2018, and 2019. And you can see basically if you have the right kind of inputs, if you have the water availability in this region, you can change the overall because in this area, the Leh district, we have agriculture only for some 10,000 hectares. And what we did, we said to the government that there is a potential you can increase it agriculture depending upon the if we are able to provide them right kind of inputs, we can increase the agriculture from 10,000 hectares to in the first phase to 2 lakh 3 lakh hectares. So that is the potential we are having, and we have also demonstrated in our farm. This is a farm at Ladakh we have, and it is just adjacent to the Manali road. You can see it here how things have changed, and the willow plantation is being done there. And also if you, because a lot of water I was already saying goes as a runoff, it is not used by the people, and you get such kind of, if you use your water and try to recharge it in the groundwater, you can save a lot of this runoff, and lot of sediments you can be saved because of that. So now this is one of the studies we have carried out for finding the appropriate, using remote sensing and GIS, finding the appropriate location of groundwater harvesting tanks, and also these water harvesting tanks where we have to use them, and different thematic maps we have developed. As you can see in this, there's a drainage density map. It tells us about the drainage, what is the number of drains per unit per square meter, altitude map of that area. These are all inputs. Geology map of that area, geomorphology map of that area. Then there is the rainfall map of that area, land use, land cover map, slope map, soil map, and also the flow accumulation map. When you integrate all these things together, I think we come up with the solutions. You can see from this figure, using satellite remote sensing, list4 imagery, the visual interpretation, digitization, LULC map, and the soil map, come up with the suitable sites for rainwater harvesting and also groundwater harvesting. And also digital elevation model has been used for determining the slope map and the flow accumulation map, and also rainfall data is to be used in this. So and also you have to use analytical hierarchy process, because when you have number of parameters, you have to give weights to each of the parameter. Like I will be telling you that in this case, if you compare between rainfall and land cover, because these are to be done actually on the field. When you go to the field and see which is more important, is rainfall more important or land cover is more important for achieving whatever objective we have to harvest water in that area. And if it is done in that manner, supposing we say rainfall is 2 times more important than land cover, so land cover will be 1/2 of that, it will be 0.5. And so in this way we develop these tables, and then normalizing the tables and giving weights to each of the parameters. Supposing for rainfall, this 0.28 is the value, land cover for flow accumulation, this much is this, slope, this much is there, soil texture, this much, and so on, we do in this. And then using the ArcGIS, we try to use the multi-criteria evaluation, giving the weights to all those parameters, and come up with the, and you can see here the normalized weight that have been given to slope, the geology, the precipitation, the drainage density, and also the subcategory we have. If we have slope less than 10%, and if we are talking about groundwater harvesting, what will be the rank for that? All that is to be fed in this, and ultimately we come with this map. For example, you see this is the groundwater harvesting map. Using all these remote sensing, GIS, all the tools we have, come up with the areas which have high this groundwater availability, and also pointing the exact what is the groundwater availability in these regions. Similarly, this is about the Snowmelt rainwater harvesting. We integrate all these maps together and come up with the sites which have high snowfall, high rainfall, low rainfall, and come up with the exact locations where we are going to go for harvesting of this water. And you can see in this. And Again, this is another that is in the saffron growing area that has been done. I think also doing this groundwater kind of survey. Again, we are using softwares that have been developed from outside, using them to our conditions. Although they have the input parameters, but still we would like to see some of the softwares, especially in the agriculture, which can be used here. For example, this is a groundwater software, GMS Aquavio. It has been developed in USA for seeing how the groundwater is behaving, and if there is a climate change scenario, supposing there is an increase in precipitation, there is a decrease in precipitation, there is an increase in well discharge, there is a decrease in well discharge, how overall things are going to change in this. And all these things, and to develop the shape file of that, to see what is the land use land cover in this, what is the recharge that is taking place from this, what is the discharge, what is the evapotranspiration, soil balance, and you come up with certain scenarios that give us an idea that how things are going to happen in the future. Now, this is the squash farm we have, and we have to see the variability in this, how supposing you can see in this organic carbon, how organic carbon is behaving in this area, what is the nitrogen, and if you have some critical areas, we'll be able to identify those critical areas, what kind of interventions we have to do in these critical areas. I think I have taken a lot of time. I think I have how much? 15 minutes more?
Yes, sir. If you want to stop in 15 minutes, it is up to you, sir.
Okay. So basically saying in a field, what is the pH in that, what is the organic carbon, what is the nitrogen, what is the phosphorus, what is potassium, what is sulfur, and coming up with these tables, what is the descriptive statistics of soil fertility parameters, pH, OC, N, P, K, and ultimately developing the semi-variograms for all these parameters, OC, N, P, K, sulfur, and so on, and ultimately coming with these special variability maps, how to find if any area is having some critical decrease of some particular parameter, supposing pH we are talking about, OC we are talking about, N we are talking about, P we are talking about, K we are talking about, S, and so on. And even at the lowest level, so field level also, we can make use of these to find what is the amount of nitrogen we have having in a particular field, what is the amount of phosphorus we are having in that particular field, what is the amount of potassium we are having, sulfur, and other things that have been done. Similarly, NDVI is a very important tool that we have to see when we talk about the evapotranspiration, and how to calculate the NDVI values based on the crop coefficients. This is based on this is the flow chart for it. And we can see this, the Kc and the NDVI values, how they vary. How Kc is basically the crop coefficient, how crop coefficient varies with the NDI, and the results that have got in this are much better than what we got in the other methods. And this is the Kc, this is how it varies in the field itself. And also see the disease infestation depending upon the NDI, normalized difference vegetation index, how it is varying in the field. And you can see the site-specific nutrient management is facilitated by geo-reference maps generated by spatial interpolation algorithms embedded in GIS software. One of the limitations of the geospatial modeling accommodate, and I think I don't want to read it now. Now also crop models, they also play a very important role in this, how to diagnose a problem. And all these models have been developed outside. I'm saying this again and again. The precision agriculture, optimized water and irrigation management, soil fertility management, gene-based modeling, climate change, land use change analysis, yield production, biofuel production, climatic risk assessment, and so on. So crop modeling concepts, how they take place, you can see from this. Now aquacrop is one of the models that is being developed to how to give irrigation to the crops. So these are some of the inputs that we need for this crop model: the climate, the crop management, soil, groundwater, outputs of the aqua-crop model, the green canopy cover, crop transpiration, above ground biomass, crop yield, and so on. Now develop recommendations to improve water use efficiency, conduct field experiments to assess yield response to water, run simulation with aqua-crop. So this is another kind of a software that we have, that is DSAT, that is used for, again, it is being used to see how crops grow and come up with some policy decisions in this. And you can see we can simulate and also measure what is the yield, how different things are varying in this, what is the soil moisture content, and even the planting dates. If you have different planting dates, how it is going to affect the yield of the crop. And the water savings, you can see how water savings can be done in this. And this is, I think, this is my last slide I was talking about. So in the conclusions, I can say that optimal utilization of input resources will enhance the production, productivity, and profitability in agriculture. Precision farming, smart farming is the technology-driven agriculture. Remote sensing and expert systems are suitable tools for precision agriculture. Smart technology needs to be transferred to the farming community. Thank you very much, sir. That's it from my side.
Thank you, sir. Thank you very much, sir, for giving us insight about precision agriculture and farm agriculture.